Hi everyone, myself Bidyutlata Sahoo, working as an assistant professor in the Department of CSC Artificial Intelligence and Machine Learning at Institute of Aeronautical Engineering, Hyderabad. This is my 40th video lecture on the course Applied Artificial Intelligence. Today I am going to discuss about the planning to move in robotics. Already I have discussed in robotics after my previous videos, introduction to robotics, different types of robots, and the robotic hardware and robotic perception. This is the fourth topic in the chapter robotics. So planning how robots plan to move. These are the topics to be discussed. Motion planning in robotics, first I will discuss. Then what are the key concepts for planning, making the plan by the robot? What is the purpose of motion planning in robotics? Then different types of motion of robot. Workspace in robotics and configuration space in robot motion planning. These are the two different versions, like workspace, the physical space of the robot, and the virtual space of the robot as well. Then I'll discuss the different approaches or the core approaches to the path planning. This is the topic learning outcome for this particular topic. So after the completion of this topic, students can discuss the motion planning algorithm to determine the feasible and collision-free paths for a robot to move from a start position to a goal within a given environment. Let me discuss what is the meaning of motion planning in robotics. Like, if you compare with the human being, when we want to go somewhere, we used to plan how to go from our initial state, from our home to the destination, whether we'll go by walk or we'll go by car, or we'll go by car, then we'll change to flight or something. So like this, we used to plan. The same thing happens for the robot also. So that is called as planning of the movement, or it is also called as the motion planning in robotics. So motion planning in robotics, it involves how to move a robot effectors like the arms or the wheels to perform the task or to reach the destination. In my previous videos, while discussing about the robotic hardware, I have discussed a few hardware components of the robot, like the sensors. Sensor is one of the hardware. Another component is the actuators and effectors. So sensors through which it receives the input, the robot receives the input from the environment. Actuators, it performs the action in the form of transitional movement or the rotational movement. Means transitional movement along the x-axis, along the y-axis, along the z-axis. Then rotational movement along all these three axes, rotation about x-axis, rotation about y-axis, and rotation about z-axis. So all these movements are possible with the help of actuators, and end effectors are nothing but the tools which are used to hold the object, or like the screwdriver, or like picking the object from one place and keeping another place. That is done by the end effectors, which are called as the arms or the wheels. With the help of arms and wheels, robots can perform the action. So that is why, motion planning in robotics, it involves determining how to move a robot's effectors to perform the task or to reach the destination. So that is why it consists of the arranging a sequence of actions to achieve the specific goal. So directly the arm, suppose this is the robotic arm immediately cannot reach to the object. It has to move in different directions. Either it may move in the forward direction, then it may move in this direction, or somewhere the rotation is needed. So all these steps are needed, which are called as the arranging of sequence of actions. So to perform any particular task by the robot, this sequence of actions are needed by the end effectors. That is called as motion planning. Now, the main key concepts for this motion planning are of two ways or two types we can say. One is the motion planning, which is also called as the path planning, which is done by the robot. Another one is the algorithm input or output. Any one method can be used depending upon the type of robot. So path planning or the motion planning, it is nothing but a computational problem focused on finding the valid sequence of movements that guide a robot or object from a source to the destination in a physical space. For example, the mobile robot navigating inside a building must move while avoiding the walls or stairs. That means the robotic software, all the sensors, effectors, and the end effectors, all the hardware components should be configured in such a way that all these steps it can recognize in advance before performing any action without colliding anywhere. And algorithm input or output, I mean, in the first case what I told in the motion planning and path planning, it needs to the robot has to plan based upon the configuration of the software for the respective hardwares. Another way is there algorithmic input or output, means a particular algorithm may be used for a specific robot, and the input should be given, and based upon the input the output will be performed by the robot. Now input is the task description like the environmental layout or the obstacles, that is called as the input, and the output is the commands for speed, direction or turning, like wheel control for a mobile robot. Now if you take the example of the robotic vacuum cleaner, every time the robotic vacuum cleaner cannot work for different houses. It can work for a single house, and but before making it functional, we have to configure the robotic vacuum cleaner with the configuration of our house, or with the layout of our environment, like how many rooms are there, where is the sofa, where is the bed, means all the obstacles, where like it has to clean complete floor. So all the location of all the like tables, chairs, beds, we have to configure initially. Once it is configured, the same time we should not repeat for next time, and the robot can continue for the cleaning of the environment or the floor. So that is what it is called as algorithmic input or output. So before starting of any work, first time configuration is needed. That means input should be given to the robot, and based upon the input, then the robot will take the decision and robot can continue its work. So these are the two ways the planning of the robot can be performed. Now, the main purpose of the motion planning in robotics is it ensures the safe and efficient movement by generating the collision-free path. This is very important. Generating collision-free paths and accounting for physical constraint like the stability and kinematics. The main important thing here, the robot's movement plan, it should be done in such a way, whether it is using algorithmic input or output, or it is using the motion planning or path planning concept. The main thing is it has to move in such a way that the robot should be safe, and the movement should be the efficient, and it should be collision free. Should not hit to any obstacles. That is the main important purpose of the motion planning in robotics. Now, there are two different types of motion planning are there. One is the point-to-point motion, another one is the compliant motion. Then what is the meaning of this point-to-point and compliant? Point-to-point means movement where the robot navigates from a starting position to the target location without physical contact with obstacles. Means whenever we are configuring our robotic vacuum cleaner, we have to configure in such a way that if we give the correct input, means if in our drawing room what are the objects are there, in our middle room what are the objects are there, or in our bedroom what are the objects are there, and its location and their configuration, means the size of the object, then if we give the correct input, definitely it will not hit to that object, and it can clean the floor without contacting with the obstacle. That is called as point-to-point motion. Basically, it is used for the task requiring the precise positioning. Precise positioning means the correct position of the object in the environment. For example, a delivery robot moving to a specific coordinates, and a robotic arm reaching for an object on a shelf. So these are the examples of the precise positioning, and it focuses on the collision-free path planning. Okay, so point to point means the movement path or the motion planning should be done in such a way that it can move from starting from the start position to the target position without hitting or without any physical contact with the obstacles. So compared to this point to point, one more is there, that is compliant motion, that is the opposite of point to point. So here the robotic movement can be done where the robot can interact with the obstacle or the environment through the physical contact. Now you can see here, without interacting with the obstacle, the robot cannot perform the action. That is why it is called as the compliant motion. Now you can see the example here, a robotic arm screwing in a light bulb, or else a robot pushing a box across a table. So whenever a robot pushing a box across the table, definitely robot's arm needs to touch the box and it has to slide the box on the table. So that is called as while performing the action, whenever robot perform the action through the help of actuators and the end effectors, it will have the physical contact with the environment. So that type of movement is called as compliant motion. So it combines the motion planning with force or torque feedback for controlled interaction. Now, let me discuss about for this type of motion planning or the path planning, whether it is a point-to-point contact or point-to-point motion or compliant motion, doesn't matter. But there are two things are considered during the configuration of the robotics. So first one is the workspace, second one is the configuration space. Workspace means what? The workspace is nothing but the physical space or the real world physical space where the robot is present. But the configuration space is where the virtual space, how the robot works. Now, robot is present. Suppose the screen is the robot that is called, and it is present in this room, that is called as the physical space of the robot, physical location of the robot, that is called as the workspace. And a robot knows that where are the obstacles surrounded by the robot or surrounded by it. Whereas the virtual space, how we can say it is a virtual space? Whenever it works or whenever it moves from one place to another place, all the hardware components should be configured with that virtual space in the form of software. So that space will be divided like a screen. Now you can understand very easily if I take the example of our screen, TV screen, how the pictures are visible very clearly, because the picture is divided into a number of cells, that too in the form of rows and columns. And if the rows and columns, that the intersection between the rows and columns, if they are very wider, then picture quality will not be very clear. If the intersection between the rows and columns are very thin, means very negligent, then in that case we can say the picture clarity, the pixel size, the clarity of the resolution of the picture depends upon the size of the pixel. If the pixel size is very small, definitely the clarity of the picture will be very good. So the same way here, the virtual space is also divided into a number of grid. Anyways, I'll explain. So let me discuss about the workspace in robotics first. So this is the real world physical space in which the robot operates. So it includes everything around the robot, like the wall, furniture, obstacles, and the robot itself. For example, if a robot arm is working on the table, the workspace includes everything, including the whole table, the object which is present on the table, and the air around where the arm can reach. So everything, including the robot itself and its surrounding, considered as the physical space, or it is considered as the workspace. The actual 3D. Now this workspace, either we can represent in the form of 2D format, or else we can represent in the form of 3D format also. 3D format. So if it is a 3D, how we can represent in 3D environment? Using the Cartesian coordinates of X, Y, and Z. Now, configuration space in robot motion planning. So, configuration space, as I told, it is the virtual space compared to the workspace. So first we should know problem should to configure the software of any hardware component of the robot. Problem should be represented in a precise way. So that is why the first step of the configuration space is problem representation. So this is the first step in which the motion planning is finding an appropriate representation where problem can be clearly described and efficiently solved. Now, raw 3D space is often inadequate for complex robotic systems. Now, you might be thinking why when workspace is there, what is the need of configuration space? Because in every situation, it's not like robot is very small or it is very minute and it can be accommodated in every environment. It's not possible. That depends upon the situation where the robot is working. If the robot is working for the mining or if the robot is working for undersea exploration, then in that case the space should be very vast and which will not be visible for the robot at a time. So in that case the 3D space, the configuration in using 3D vectors, it would be very difficult for the complex robotic system. So that is why to understand or to make it comfortable movement, so instead of 3D space, we can go for the configuration space where the vast area can be configured within a small space, which is called as, that too virtually in the form of software, that is called as the configuration space. Now the second step, after defining the problem clearly, then we need to understand the configuration space will happen. So configuration space is nothing but a mathematical space representing all the possible states of a robot. Like what are the states then? First one is the position of the robot using all three dimensions like X, Y, Z coordinates, and their orientation, the angular movement of the robotic arms or the mechanical arm along the X-axis, Y-axis and Z-axis. Already I discussed in my previous class, if the rotation happens along the Z-axis, that is called as air, and if the rotation along the Y-axis, it is called as the pitch, and if the rotation along the X-axis, it is called as the roll. So orientation should be mentioned and all the joint angles for articulated robots. Now you can see the example here for a robot arm with two joints. C space might be a 2D graph where each axis represents one joint angle. A point on the graph shows a specific position on the arm. That means the configuration space, it's not only 2D space or 2D graph. Configuration space can be represented in the form of, first of all, it can be represented in the form of grids. Okay, after representing this grid, then the location where the robot will move, like the free spaces and the occupied spaces will be identified. So wherever the free space, suppose this space is free, this space is free, this space is free, this space is free, then robot will plan by observing these free spaces for its movement. So after that, these free space observations will be converted in the form of graph. That is why this type of space is called as configuration space. Now the third point is path planning in configuration space. After the first step like problem definition or like defining the problem, then configuration space is identified, then path will be planned by the robot, which is called as path planning in C space. So the core problem becomes finding a continuous path between the starting state to the ending state, which is called as the goal configuration or the desired state. So it must satisfy all the points along the path lie within the valid C space and no collision with obstacle represented in C space. Like path planning, as I told, after defining the problem statement, the configuration space in the second step, the coordinates, the orientation and all the joint angles will be defined. In the third step, all these points, like the points which are free in the space will be identified for the valid path, and all these points should lie inside the configuration space only. So no collision with the obstacle represented in the configuration space. Now let me discuss different approaches are also used for this path planning by the robot. One is the cell decomposition and the second one is skeletonization. So cell decomposition, what it says, like our TV screen, how it is divided into a number of cells, and each cell is called as a pixel or the grid, and the size of the grid, the resolution of the picture, the clarity of the picture, that depends upon the size of the pixel. If all the pixels are very close to each other, then definitely the clarity of the picture would be good. Same thing here, the cells are the complete configuration space is divided into a number of cells. So it divides the configuration space into a discrete number of cells, which are called as the grids or voxels. So the process is here, like the environment is partitioned into a finite number of cells like this, like a grid type of structure. Then each cell is labeled as free or occupied. So that depending upon, if suppose previously it is occupied, then it is occupied, this is free, occupied, this is free, this is occupied, that's free. Like this, it would be level, and path is found by navigating the connected free cells. So this is the free cells, it can be connected like this. So this is the path can be created by the robot for its movement. That is called as the cell decomposition. So here few characteristics are there for the cell decomposition method. First of all, in this cell decomposition method, definitely resolution complete. Resolution complete means what? Finds path if one exists at chosen granularity. That means definitely the robot will find a path if the path exists, means number of cells. If the number of cells are free, definitely it will find a complete path starting from the starting location to the destination location. And simpler implementation, but memory intensive, but for high resolutions. Implementation would be very easy because it is just connecting the free spaces which are available in the configuration space, but it may consume more space, memory intensive for high resolution. Okay, sometimes it may consume more space for high resolution task. Compared to the first one, cell decomposition, the second one is skeletonization. Skeletonization is nothing but it extracts a topological skeleton. It's not the simplified representation of the cell decomposition, we can say. The process is like it reduces the free space to critical connectivity features and creates the graph of key points. As I told, in the cell decomposition, only the free space will be connected by the robot to find the complete path. Whereas after connecting the free spaces to find the path, then that free spaces, the complete path will be represented in the form of graph, either Voronoi diagram or visibility graphs. So that is why the name is called as skeletonization. The characteristics are it preserves the connectivity while reducing the dimensionality. The space can be reduced from 3-dimensional to 2-dimension, or from 5D to 4D or 3D, and it is more efficient for complex environment. So this is the concept about these particular topics. I hope you might have understood. For the preparation of this topic, I refer this Russell Peterno big book. The picture which is available on the screen, as well as this YouTube website, you can also follow. I hope you might have enjoyed. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.